Alright, 11-2 arcs and chords. We're going to learn to apply properties of arcs and chords. There is this thing called a central angle. I believe we've talked about it before. It's an angle whose vertex is the center of a circle. And an arc is an unbroken part of a circle consisting of 2 points called the endpoints, and all the points on the circle. It's going to be important that it's on the circle between them. So, kind of with this minor arc, there's two kinds of arcs. There's a minor arc and a major arc. And a minor arc is the smaller of the two arcs, because if what you're doing is basically you're cutting the circle into two pieces using this central angle. So ABC, that angle right there, this angle X, that's a central angle. That cuts the circle into two pieces. There's this piece right here, and then there's this bigger piece going in the opposite direction. This smaller piece right here, that's my minor arc. Okay, and here are the different ways. This is how you would note it. The measure of measure of arc AC. Notice that this right here, that little curve, that tells you that you're talking about an arc. Major arc, that's this bigger piece over here going this way. So this would be my major arc. And it kind of since they have the same endpoints, this A and C, to make them different, we insert this third point. So this would actually be called arc ADC. Okay. So if it's a minor arc, it's going to just be denoted with 2 points. If it's a major, it's going to have 3 points. Okay. Now, if the endpoints of an arc lie on a diameter, then it's a semicircle. So if EG is a diameter, then we would say this arc is a semicircle. And the measure is 180 degrees because half of 360 is 180. All right. So that's just another reminder to you about the minor arcs and major arcs and semicircle. I just rewrote it for you. All right, so let's just practice some basic notation. The central angle is going to be angle LEY. Of course, you can rewrite it. You can also say angle YEL. Alright, the minor arc would be arc LY. The major arc would be arc LUY. Or again, obviously, you could also start with Y and go the other way, YUL. Same thing. Okay, adjacent arcs are arcs of the same semicircle that intersect at exactly 1 point. So I have arc RS and I have arc ST. So there's this thing where I can do what's called an arc addition postulate. So the measure from A to C is equal to the sum of the arc AB to the arc BC. Okay, it should be pretty straightforward, common sense. I'm just adding these two pieces that are connected. They're joined by this point B. I can add them together to get this bigger arc. So here's an example. We want to find the arc, the measure of arc BD. Okay, so I'm going this direction, and I know that because if I were to go this direction, that would be the bigger side. So that would be a major arc. This would be the minor arc. It's only got 2 points, so I got to go the shortest distance from B to D. All right. The thing with this, we're going to have to do a little bit of manipulating, I guess. This right here, this is a diameter. BE is a diameter. AC is a diameter. All right. So notice that this right here going this direction, that's a semicircle, so that would be 180 degrees. So if I wanted AFB, I would do 180 minus 97.4. That would be the measure of arc AB. Okay, the one we want is BD. Okay, now notice this right here, these two lines, I see two lines that intersect at a point. So I know this is 97.4 because I have vertical angles right here. Okay, so I need to find this little piece right here. All right, and I'm going to do that kind of going the other way with the semicircle. I'm going to do this whole thing right here that's 180. I know that's 180. And I have these two. So let's see. the measure of arc DC is what we need to find first. And I know that's equal to 180 minus the sum of 97.4 plus 52 degrees. Okay, I have 2 out of the 3 pieces. So I can add these 2 and subtract it from 180 to get this little bitty one right here. Okay, so putting that in the calculator, I get that this is 30.6. So that means, that would be degrees. So the measure of arc BD is going to be the 97.4 plus the 30.6, which comes out to be 128 degrees. Okay. All right, some more kind of information. When a circle or congruent circles, within a circle or congruent circles, congruent arcs are 2 arcs that have the same measure. So in the figure, arc ST is congruent to arc UV. That's just saying that it's possible you can do that to have congruent pieces. All right, so that pulls us up to these theorems. If I have in a circle or congruent circles, that means I have 2 same-sized circles. If the central angles, if angle EAD is congruent to angle BAC, then that means that I can connect these 2 points that are on the circle. So I get this chord BC and I get this chord DE from those angles. If the angles are congruent, that means these chords are congruent. Okay? And then also if I have 2 chords that I know are congruent, then the arcs that are formed by those 2 segments are also going to be congruent. Congruent circles, if I know that the arcs are congruent, that means the central angles are congruent. I'll kind of show you what that means. We'll go through some examples to kind of explain what those theorems are actually saying. All right, so I know that TV, this chord right here, is congruent to this chord down here. So that means this arc from V to T has to be congruent to this arc WS. Again, I know these 2 arcs are congruent because these 2 chords are congruent. So to solve for this measurement, I would do 9n minus 11 equals 7n plus 11. All right, moving things around, I would subtract the 7n. That gives me 2n on this side. I would add 11 over here, so I get 22. That tells me that n is simply 11. Be careful with this because I'm not asking you for the variable, I'm asking for the measure of arc WS. So that means I have to substitute that back into the problem. So 7 times 11 is 77, plus 11 more is going to give you 88 degrees. Okay? All right, some more good stuff. Some theorems, again. If a circle, in a circle, if a radius or diameter is perpendicular to a chord, then it must bisect the chord and the arc. So if I know CD is a radius, and I have some chord EF, and I have this right angle, that means ED is congruent to DF. It also means that arc ED is congruent to arc EF. Okay. In a circle, the perpendicular bisector of chord is a radius. So kind of going back the other way, if I know these 2 pieces are congruent, that tells me this line right here is a radius or a chord depending on how long it's drawn. If it goes from A to K, it's going to be radius. Obviously, if it goes from J to K, that would be a diameter. Okay, so let's look at an example. All right, I want to find the distance from N to P. All right, so notice what I can do. I know that RM is a radius because it's going from the center to the edge. So I can draw that right there, draw me another radius, because I know this angle right here is going to be 90. So 8 plus 9 gives me 17. So all my radii are 17. So now I have a right triangle, which means I can use Pythagorean theorem. So since NR is the hypotenuse, that's going to be 17 squared minus 8 squared, which is going to give me let's make that b squared. That's going to give me 225 is equal to b squared. B is going to equal to the square root of 225, which is 15. So I know this piece right here is 15. All right. Now I got to do the same thing on this side. But I notice this is another radius, so that's 17. And I still have this segment that's 18, so this is going to be 15 also, which is kind of what this theorem is saying right here. I know these two pieces have to be congruent, so 15 plus 15, or 15 times 2, that's going to give you 30. That has to be in P. Distance from N to P is 30. All right. Now we got to do QR, which is this thing. And that's a radius, so I can draw that again. Draw me another radii. Go in both directions. That means this is going to be 20 and this is 20. All right. Pythagorean theorem would tell me again 20 squared minus 10 squared is going to give me that other side squared. 400 minus 100. That's going to give me b squared is equal to 300. B is going to be equal to the square root of 300. And this one does tell me to round, so I can put that in the calculator. Square root of 300 comes out to be 17.3, or about 17.3 since we're estimating. Oops, I'm not done yet. That means that would be 17.3. But we don't want to round to the end, so let's do times 2. That gives me, actually, that QR rounded to the nearest tenth is going to be 34.6. Okay.